Okay, thanks again for the invitation. It has been exciting as far as I could follow. Not everything, but I saw the last two talks, so excellent work, George. Also love to see the updates. Today I want to speak a little bit more about soft robotics, and thank you for that pitch. The last couple slides were super inspiring. I don't feel so much like an oddball now in this community, and that makes it much easier for me. In particular, I would like to talk about an issue that concerns us all and how to become more sustainable, both in the field of soft robotics, but also soft electronics. And here in soft electronics, some people, like the field is a lot further already. And thinking of the excellent work on transient things that John may be showing a little bit later today as part of his many things. But in soft robotics, there's not yet such a topic. And we picked up on this a couple of years back. And some of this I would like to share with you today. Yes, where I am from, who are we? I'm heading the soft matter physics group and the soft materials lab at Johannes Kepler University. You can see that in the center here. We are basically in the center of Europe in Austria, a little guitar-shaped country here. Typically, people don't find us in Linz. They would go to Vienna and to Salzburg because of all the Mozart and all the nice culture. But I would like to say that Linz is also nice. We remodeled our campus. Now we have like even a terrace on top of the building that we are sitting in. So should there be the opportunity to come visit us soon again, and I think now most of us are vaccinated, we are heading there. You're very welcome. I would like to see any of you. Once you come to Austria, I would be happy to host any of you to come to Linz. The research in my lab focuses on sustainable technologies, both on the material side, but also on the energy harvesting and generation. I might talk a little bit about it today. You see this solar plane, we have a huge subgroup that works on organic and perovskite photovoltaics, but I'm not going to talk about this. My background is in ultra-thin and lightweight, so to say imperceptible electronic foils. When I did my postdoc with Takao Sumeya in Japan, this is where a lot of this work comes from. And lately we ventured into, in general, soft electronic devices and soft robotic devices. The credit goes, of course, to my marvelous team, because I only get the pleasure to talk to you about all their achievements. Typically, we would also meet in the conferences, but for now, this is not possible. So I would like to extend my thanks to all of them. They do all the work, they deserve all the credit. Why do we want soft technology at all? And George has mentioned it already. It has a lot of huge advantages. And typically one looks at this chart where you compare performance to specialization. And we have already out there in industry all around us, extremely specialized, very high performance conventional robotics. Those are excellent, those should be used for the tasks that they're designed to. And on the other hand of the spectrum, we have these beautiful inspirations from nature, like the classic octopus or the elephant trunk, that is extremely versatile soft machine made out entirely of organic materials, of soft materials. And soft robotics basically tries to bridge this gap. We take a lot of bio-inspiration, but we mostly take conventional materials, and we would like to realize something in between. A main focus is, of course, in the healthcare area, and especially in the human-machine interaction, but also in assistive robotics, wearable robotics, things like this. I think this is where we will see and hear a lot more in the future. But also the simple handling of soft objects is something that people are targeting a lot with the soft embodiments. Now, we have outlined what one would need for the ideal soft robot a couple of years back in this focus article where in Science Robotics where this is taken from. So if you look at the natural inspiration, you have the soft materials, but you also have the energy basically remotely distributed. You have the actuation remotely distributed, you have the sensing distributed, and you have the brain basically also to some extent into this in the soft devices. The combination is now sometimes called, physical or materials intelligence, because the soft materials easily adapt to their surrounding and they don't need so much control algorithms. So many of the things you can take messages from and you can expand and create your soft robotic device. But at the same time, one should think about the amount of waste we're actually creating with this very, very quickly evolving technology that is basically now penetrating every aspect of our life. And only electronic waste for 2021 is expected to reach already 140,000 tons per day. Now, to put this into perspective, this is about the mass of 14 Eiffel Towers per day, just on electronic waste. And we believe this is not the way to go. And especially if you're thinking about healthcare, there are many, many one-time use applications that you can think of that will become maybe a waste problem in the future a lot. And the challenge that we tried to meet, or we were all facing, is that we want to take the best from both worlds. So we would like to have materials that are on one hand sustainable, but on the other hand also reach the high performance that can be found in more classical materials. And my brilliant PhD students, Florian and Melanie, tackled this problem. Actually, Florian graduated a little while back and he's now a third Shia at EPFL, but it's all their work that I'm showing here. And I would also like to mention that this focus article in Advanced Materials just came out a couple of weeks ago, where a lot of the very active groups in the field contributed to the materials issues in soft robotics. I'm very happy that I had the chance to host this, this special issue together with Poissy Lee. So if you're interested in some of the current trends in the field of soft robotics, maybe that's one place where you could kindly look at. So we set out to develop an elastic material that is both extremely stretchable, extremely durable, self-adherent, but entirely biodegradable. So it is made entirely from bio-derived, gelatin-based in this case, polymers. It is tuned in such a way that it can achieve the performance that we were looking into. So with this, we were working on two ends, so to say. We would like to have these electronic batches to be from a soft, stretchable, and degradable material, but at the same time, they should be functional in soft robotic embodiments that usually tend to be stretched to at least 200% or even higher. And we restrained ourselves to using only natural and food-safe ingredients, so to say, or constituent materials, where the base of the hydrogel that we here kind of developed is gelatin. That is very well known material. I think that's known for more than 12,000 years, but you can still do a lot of new stuff with it. And it's coming back big times. If you find the right amount of sugars and additives, such as glycerol and food-grade additives and citric acid, then you can make a really, really durable material out of this that is at the same time completely biodegradable. We tested actually this biodegradability. So on the one hand, as you can see in the video, sped up video on the left, this hydrogel still dissolves in water over the course of a day or two. But this doesn't necessarily mean that it's biodegradable, because what you end up with is eventually a soup with polymer chains that are dispersed in water. And if you ingest or inject the material, then this dissolved polymer chains can very easily end up in your kidneys and don't get out of the body. What you really want is that the polymer chains are broken down. And for gelatin, that's relatively simple. That happens enzymatically, for example, through wastewater bacteria, and you can measure, or you can monitor their oxygen production over time, and then you can see that they're actually feeding on your material. And if you're hitting this 70% threshold in this specific test over 10 days, then by EU norms, the material is considered entirely biodegradable. So we had this part of the metal basically unchanged or still down. But what about the mechanical properties? Again, at the base, polymer gelatin defines mostly, the amount that you put in defines mostly how stiff it is and how stretchable it is. And by changing the concentration, you can vary the elastic modulus by about an order of magnitude. We are well within the range what's common for soft elastomers that are used for soft electronics and robotics. And you can also tune the ultimate stress and the ultimate strain. So for these dumbbell-shaped samples that we reach here is about 3.5. So you can extend it by a factor 3.5. This is quite neat. But since, since this is relatively common achieved, if we want to go beyond this and have high ultimate stress and high ultimate strain, then typically by adding sugars, certain sugars as a co-solvent, you can modulate how this gelatin network interacts with each other and how these physical crosslinks are formed. And with this, again, improve and increase the mechanical properties. However, you will still have a hydrogel, which is prone to dehydration. So in the long run, this material will not work for you unless you add a humectant such as glycerol that is also food safe. So if you add actually a lot of glycerol, if you replace basically a large fraction of the free water by glycerol, then you can achieve a hydrogel that is very, very stable in its properties. And this slide just summarizes what happens if you add enough glycerol, then the mechanical properties such as the Young's modulus would not change over the course of at least a year. So you can have this fully biodegradable material on your desk, work with it, and it will not change in properties for an entire year or beyond, unless you trigger the degradation by an external stimulus, such as, for example, wastewater that is filled with bacteria. So that was very good. And to summarize, the very basic ingredients are relatively simple, but they allow you in the right concentrations that we meticulously engineered to achieve something that is almost as good, or at least as usable as synthetic polymers, but at the same time completely of natural origin and completely able to feed back to nature one-to-one. So that's a big advantage in terms of the waste production. Since it's a thermoplastic elastomer, you can actually use heat to manufacture structures out of it, and you can even go ahead and design modulus graded substrates by using a laser to kind of assemble these structures. So the different colors here correspond to different mechanical moduli. And if you have this assembled, and you can put, for example, electronic components at areas of the batch that are less strained and the sensors at areas that are more strained, or you go ahead and make complex 3D structures that eventually are not possible with 3D printing. Or you repair your structure. If it's broken, you can just melt it basically together again, and it will work, continue to work. So with this, we designed sort of a rudimentary on-skin electronic patch that allows you to measure a couple of physiological inputs, such as temperature, humidity, and strain. And it's powered by a reusable flexible PCB. So the right side, that is not degradable in this case, but it's at least reusable, that hosts the energy in the form of a battery and Bluetooth communication and a little bit of electronics. So this is one way to go. If you cannot make everything entirely degradable, you can combine reusable components with degradable components. However, everything that is in touch with the skin is entirely degradable and can be disposed of easily. The advantage of this gel is that it also adheres on its own on the skin, so it doesn't come off. It feels like a regular medical plaster. You can put it on, you can measure. That video just shows that the functions work. And that's, so if Melanie blows on it, she changes the humidity. So the signal drops. And you can, of course, also just measure temperature by using a hot cup, for example. You see that the temperature rises in the vicinity of the batch. And of course, you can do the same with strain. I should speed this up a little bit. And once you're done, you can very easily peel off the device from the skin, and it doesn't irritate your skin. Actually, we put a little bit of, to summarize this, we put a little bit of effort in this to test how biocompatible gelatin actually is. And we wore it, so the students wore it on the hand, and they peeled it on and off again. And we found both that the skin doesn't get irritated at all, even if you wear it for more than 40 hours. Eventually that has to be extended, but still, this is how far we went for this paper. But more importantly, also the material itself doesn't degrade when you wear it on the skin. So even though you do sports, you sweat, even though it's a hydrogel, the mechanical properties actually remain intact for a certain amount of time. So this is also something that we're looking into. Then, of course, since the material is elastic and very stretchable, you can make pneumatic actuators. George has already explained how those work. Inflated tubes, basically. If you want a shape, then you can induce this by an exoskeleton that gives rise to the specific deformation. Oh yeah, by the way, you can make it glow in the dark because it's a hydrogel. You can add UV excitable dyes, or you can add other dyes, that can diffuse to the skin in it for medical purposes. But the core of this slide is down here in the middle, where it says that we could achieve about 300,000 actuation cycles. And actually, that's a lot more than what was out there before. We have thoroughly checked the literature, and with most biodegradable elastomers, people have shown maybe 10 actuation cycles so far. So we went really way beyond the state of the art for a soft and elastic material. we can, of course, also equip these devices with sensors made from the same material. If you make a foam out of the biogel and put electrodes on top, then you have a deformable capacitor. And if you have a shape change, then you have a sensor, and you can put this on the actuator to look out for obstacles like a rose thorn or something like this. But you can also work it into some sort of electronic skin that has multi-point measurements. And like this, have a pressure sensitive skin that can either detect the weight distribution or on skin works as a pressure sensor itself. Okay, I do not know what time it is. Did I lose my slides now? This is very bad. I got lost.
Yeah, Martin,
I lost slides. Yes, I pressed.
There, yes, we lost you. Yeah.
Yeah, am I back?
You're back. Yes, you have easily another quarter of an hour.
That's good. I rushed a little bit through the first part, but this is because I wanted to show you also the second part of the talk. So the first part was all about elastic degradable materials, but we are doing a lot of more things. And since it's been a time since I've been at the last conference, I thought I'd put a couple pitch slides and show you what else we have at our institute. And well, this brings me also, again, to kind of a sad story. My advisor and the former boss of this institute, Siegfried Bauer, he passed away more than 2 years ago now. And I took it upon me, together with very, very talented colleagues and friends like Shigang Su and Christoph Keplinger and many others that you see on here, to finish some of his last papers that have been at the Institute for a while. And those were on bio-inspired actuation mechanisms for very, very high-speed actuators. And the way that this works is that you exploit mechanical instability in an elastomeric membrane. And this works you're intuitively familiar with this concept if you have ever in your childhood or as a grown-up inflated a rubber balloon. Then you always see that you experience this N-shaped pressure and volume curve where at the beginning it's very hard to inflate the balloon, but at a certain threshold, basically the balloon almost expands on its own. It gets very easy to inflate the balloon and it gets very large very quickly. And this is a very typical characteristic for elastic materials that has been studied now for a while. But what you can do with it, you can actually trigger this instability with a very small input signal, with a very small difference in pressure, and achieve huge changes in shape within only a couple milliseconds. So between the left and the right balloon here, there are only 20 million seconds. So Josef and Nikita took it at heart to finalize those experiments. And I'm very grateful, especially to Nikita, who did a lot of the theory behind that to understand this all. I will not bore you with it, but I will show you, if it plays, a video that shows how really, really fast this process works. That's a slow motion video. I know that's actually a real-time video. And now we have the 10 times slow motion. So one possible application, of course, is for sorting of objects, but also for very, very fast mechanical grippers, because overcoming this instability, again, takes just a couple milliseconds. We expanded this a bit further, and Josef later showed that you can trigger this instability with the heat of your body. So you can, for example, have a vessel that is filled with a volatile liquid, like alcohol, for example, ethanol or acetone. And by heating this liquid over its gas transition temperature, it will vaporize and it will trigger this instability here. And that's another application of a soft robot that is triggered by a stimulus different to any others, just by thermal energy. This compares, I hope both videos run. This is a video that shows how it works on the right side in real view, and on the left side, you see the same thing happening in the infrared camera image, and you see that you warm the lower part of this inflatable, of this chamber, and you see the balloon here. And actually the fun part about this balloon on the top is that when it contracts, it gets cold, and when it expands, it gets hot. And this gives rise to something that's called elastocaloric cooling. And this is a paper that came out just a couple months ago now. So we knew that this works, and you have probably heard of the VanGogh effect. When you take a rubber band and you stretch it real fast, then you decrease its entropy. And by doing so, it has to get warmer because the total energy is conserved in this fast adiabatic process. And if you relax the stretched rubber band very quickly, then you actually cool it. And this adiabatic change in temperature is at the very core of every cooling algorithms. However, so far, all these machines weren't very efficient. And this was the first time that we showed that you can actually make a refrigerator based on nothing else but a rubber band. And the secret is that you need to combine this snap-through instability together with the rubber material that undergoes stress-induced crystallization, because then you have not only the entropy change through the orientation of the polymer chains, but you have also the intrinsic crystallization, which is a second-order phase transition. And if you combine these two, then you can get a device that actually cools quite a lot. So you can cool this rubber membrane with one snap-through. It takes place in a couple microseconds, actually by almost 30 degrees. That you can harvest this change in temperature, obviously, to drive a heat pump. And if you extrapolate this, then eventually you can make a refrigerator out of such kind of a device. I would just like to show you that at the snapback, it's really, really fast. And the central part of the membrane here gets deep blue, which means that it gets very cold. So we have, of course, the theory down to all of this. It's relatively complex, and I'm definitely not going to bore you with this. But if you're interested in this type of work as well, I'm very happy to share all the details later on in the discussion or at another point of time when you contact me. Something that maybe is a bit more related to healthcare devices, and actually that is something that one could discuss later, George. This type of actuators are based on sipping electroactive polymer-based devices that combine basically the pumping of a liquid with electrical actuation. So instead of using a pneumatically inflatable system with a pump, you can actually drive this pumping mechanism by applying an electric field across a membrane, across two membranes that in between have a dielectric liquid. And Christoph Keplinger, who is now in Max Planck, popularized or invented this topic a couple of years back. Our contribution here is a focus tunable lens. So by the same principle, we displace the liquid in the outer ring. Via the sipping mechanism, we change the curvature of a bubble in the middle, and we change the focal length. Again, we have a complete theoretical understanding of this, but I will not go into detail. I'm just going to show you how these microactuators work. So the electric field that you need here is just a couple 100 volts, and we know how to reduce it even further. And for this, we get quite a significant change in the focal length. But I'm very, very certain that this type of mechanisms can also be used to inflate and unroll other type of pneumatically electrically coupled actuators. We are doing a lot more with actuation, and another way of getting actuation in soft materials is by exploiting the Lorentz force. And my postdoc Johannes is pushing forward these topics, where he uses liquid metals embedded in an elastomer that are exposed to a static strong magnetic field, a static B field. And by applying a current, you basically have the Lorentz force acting on parts of these conductors, and you can get a very controlled and a very nice deformation in the actuators, and it's basically programmable. So you have sort of a way of programmable robotic matter here that is entirely soft and needs nothing else but very low voltages, well, currents in the ampere region, and the static magnetic field. So we are now working on miniaturizing this type of really, really fast and really controllable actuators. I think I'm a bit faster than I thought I would be, but anyways, that doesn't matter. Leaving more time for the others. One important topic that we always have in the lab is how to power actually all these variables. And one nice way, of course, is batteries. And since 2008, I think we are working on stretchable, flexible, mostly stretchable batteries. Some of the latest things that my PhD student Doris made was implementing very porous, but still very stretchable separator material for this type of batteries that has a much higher conductivity than regular separators. So actually the McMullin's number is very high, which means that the conductivity of the ions through the separator compared to their intrinsic conductivity is very high. The ratio is very good. And with this, we power on-skin electronic circuits that, in this example, basically connect to a smartphone, and you have a wearable remote control. This is just one example of what you can do with variable stretchable batteries and a little bit of distributed electronics in a soft matrix. And the very last thing that I will not actually talk about, but I still will show you, is that if you're interested in X-rays and their detection, then one can go ahead and use actually perovskite solar cells or perovskite photodetectors to detect them. And it's the only thing about this type of material that I'm going to show. So if you make ultra thin and lightweight X-ray photodetectors, then they're very sensitive to X-rays and they're also very conformable. So this is something that Stepan and colleagues around Beatrice Fabiani in Italy are working, still actively working to develop this concept further. So the next generation of your X-ray tubes are eventually going to be fully variable and conformable. Okay, with this, I would like to thank some of my senior collaborators and of course, the funding agencies, you for your kind attention, and big thank you also to Siegfried for his guidance and for his many contributions throughout the years to all the soft devices that I was able to show you today. Thank you so much.
Martin, thank you very much for the excellent talk. The floor is open for questions. You can either post them on the chat or unmute yourselves and ask a question. Do we have any questions?
Hello.
Yes, please.
Yeah,
go ahead.
This is Zhao Zhao speaking from company Huawei. Yeah, so I see many interesting topics from professor. So maybe I propose I could have a follow-up detailed discussion with you. And here I have just two quick questions. One is that how efficient is the heat pump that you mentioned? The second question is I noticed that the tunable lens has like 500 voltage, driving voltage. So is it possible to reduce down this voltage? Thank you.
So for the first question, the efficiency, so this is usually reported as COP or coefficient of performance. That's at 4.7 for this type of single stage devices. This is kind of okay. What's more impressive is the specific cooling power that is 21 watts per gram. That is the highest ever reported. And also the specific heat flux through the membrane is at 260 milliwatts per square centimeter. All of these values are extremely good for solid state cooling approaches. So of course, the next step is to do a multi-stage system and to use regeneration. But for a single device, across the list of all the caloric materials, these are very good values. And for the second question, the voltage. You were asking about the voltage of the lens, right?
Yeah, the tunable lens, yes.
Yes, exactly. So the voltage, I don't know if I can show this again here. Sure. Yes. So the voltage is linked, this is the threshold voltage. Basically, it's linked to materials parameter that you can tune, and the most important are the thickness of this sipping electrodes, so the dielectric thickness, the dielectric constants of the film, and all of this you can tune. So this is regular off-the-shelf polymers that are not very thick. I think they're just 12 microns for the sipping electrodes, but you can imagine that you can reduce the thickness. So this is very active research in the field of this type of actuators. 500 volts is, for this type of actuators, very low, but this is not the end of the line. I think you can go probably a factor 10 lower if you know all the tricks. But keep in mind, this is what I want to add. These devices only require high voltage, but literally no currents. So this is actually not dangerous. High voltages per se are not dangerous. What's dangerous is high voltages and high currents, or high currents and low voltages. So if you think about, undressing in the dark, you are easily flashed by the electrostatic discharge that has 20 kilovolts, but it doesn't harm you much because there is almost no current in it. I hope that could answer a little bit of the questions.
Thank you, Martin. Thank you very much. Are there any more questions for Martin? Going once, going twice. That's it. Let's thank Martin again. And if there are any more questions, please add them on the chat. Thank you, Martin.